Hi there, everyone. Welcome to today's Snow Day catch-up edition of CS 475. In today's video lecture, we're going to be talking about concurrent programming models. Now, this is taking a little bit of a departure from where we've been the past few lectures. So just a review from the past few classes where we've been talking about different kinds of locking strategies. We started off with this coarse grain locking strategy where there was only going to be this single lock that we used for all CPUs that were accessing some common shared data. In this case, we were talking about this set, a linked list that was implementing a set interface. By having that one lock, we only had one, so if we had a whole lot of threads that were trying to do things on this list, even if they were not going to be conflicting, maybe one thread wanted to look at A and another thread wanted to look at D, still we've got this one big lock. Threads are going to be stuck sitting around contending on that one shared resource. So this was a simple kind of policy to implement, but we talked about how having this coarse grain locking can give us a bottleneck. Last week we built on coarse grain locking to talk about fine grain synchronization, where instead of having just that single lock that guarded this shared resource, we split up that big resource, this big list or set, into independently synchronized components. And then we were only going to have a problem if two threads were hitting the same part at the same time. The locking strategy that we talked about here was this hand over hand locking where each thread, as it traversed down the list, starting from the head node and then moving on to the next, moving on to the next, moving on to the next, always held a lock on the current node that it was traversing and its predecessor. We talked about how it was particularly important that threads all acquire their locks in the same order to avoid deadlocks too. We talked about optimistic synchronization on Monday. This was, we had the bad joke from the textbook with the tourist in a foreign land, a taxi driver who wouldn't stop at red lights, but would only stop at green lights. The idea with optimistic synchronization was maybe we can do a lot of work without any locks. Hope, we're not going to have any kinds of conflicts, nothing bad might happen. We can run through that red light as long as no one's coming, right? But then we have some mechanism to check and validate to make sure our work was successful. In this approach, we said that a thread could traverse the list. So starting from the head, it could look at the head, then it could look at the next, then look at the next, and look at the next, and look at the next, without having any locks. And then when it found its position where it wanted to do some work, like in this case, the CPU would like to add C, which should be between B and D, it would lock B and it would lock D, and then it would check to make sure that B was still on the list, because maybe B was deleted because it wasn't locked. And it's also going to check to make sure that B's successor is still D, that B still points directly to D. Because again, it could have happened that while we did not have the lock on B or D, some other thread came in and did something bad here. And the last synchronization strategy that we talked about on Monday was this lazy synchronization strategy, where we could postpone the hard work. And in the case of the list traversal and the list operations, we discussed that the trickiest part was deleting something from the list. Because when we deleted something, that's when we could potentially mess up those pointers. And that's why we had to do this optimistic traversal where we could get through without having any locks, but then we had to go back and start from the beginning to make sure that things were still in the list. And we said that we could simplify this decision so that once our CPU takes out those locks on A and B, and it can determine without having to retraverse the entire list if A is still on the list or if B is still on the list by checking this mark bit, this special mark bit. So today we're pivoting a little bit from talking about fine-grained, low-level kinds of stuff with synchronization and what locks we're taking out. And instead, we're going to talk about how, at a higher level, we can design our programs for parallelism. So given some task that we have to do, how do we decompose that task into some concurrent software, regardless of what kinds of locks we end up taking out? So the high level goal, right, is we want to make our programs faster. We want to increase performance. So let's start off at the beginning with what we can do that might impact the performance of our software and the kinds of limits that we might run into. So at a high level, we might consider limits that are imposed by physics. For instance, if my computation requires sharing data over a network, and I'm sharing data amongst several computers, and they're geographically distributed, say, across the continent, there is no way that I can get data between those two computers faster than the speed of light. Done. I probably can't get very close to the speed of light, but there's a limitation here that's physical and we can't surmount. We have limitations imposed by technology, like for instance, CPUs can only get so fast before they melt. And we have limitations imposed by economics. Like for instance, I could buy 1,000 computers and split up my task and run it on all 1,000 computers. But I would really need to have a lot of money to buy all of those computers, right? So we might be resource constrained because of those costs. So these different kinds of limitations force us to make trade-offs. Like, for instance, we can't make chips that get much faster than we have right now because it's increasingly hard to dissipate the heat from them. Um, and we need to serve so many clients, but we can only spend so much money on buying new processors and faster CPUs and having more CPUs. So this is kind of the space that we're working in. Let's talk about performance metrics and how we're going to decide that our systems are doing good or not when it comes to performance. So there are a few ways we can measure the performance of our system that have to do with the resource utilization. So that would be maybe the capacity of the service and the utilization of the service. Capacity is a consistent measure of our service's size or amount of resources, right? So we write some code that runs on a computer. The computer runs at 2 gigahertz, and because of that, and because of how my code is architected, maybe it means that I can process 100 requests per second. That's our capacity. The utilization is the percentage of that resource that's used for a given workload. So the capacity of our system might be that we can process 100 requests a second, but maybe we're only utilizing half of it right now. We're only processing 50 requests per second. And then these are two metrics that we're going to control a little bit more and focus on are latency and throughput. So latency represents how long it takes some input to propagate through a system and get an output. Latency is the time between when the user says, I would like some result, and the user gets that result. Throughput is the total amount of work that's actually completed in some given time unit. So we might measure throughput in terms of requests per second or calls answered per second. And latency would be measured in terms of how many seconds for a given call it takes to get a response. So capacity and utilization, we normally adjust by buying or selling more resources. If I would like to be able to process more requests, I would like my capacity to go up. This is a static measure that's based on how good my code is and how many computers I have, right? So we can adjust this by using our economic lever and buying more stuff. Latency and throughput are what we're going to focus on today for our discussion because these really have to kind of think hard about the problem and how we decompose the problem in order to address them. So let's talk about latency. If we have a client-server model where we have some client, like in this case, a camera, and a server that's maybe some image processing service, then latency is simply the time between when this client makes a request and then eventually they get the response back from the service. So what are the factors that contribute to latency? It might take some amount of time on the camera on our client just to send some message. There might be some time inside of the service here where once that message is received, it has to get processed. There might be some latency in getting that response back to the client too, as it flows over whatever this pathway would be. When we add multiple components and pipeline them together, the latency is cumulative. So in this picture, we have the latency to send the data from the client to the server. We have the latency in maybe this phase one of the image service, the latency in phase two, and the latency in returning it. So because this is cumulative, we add all of those times up. So we could say that the total latency and how long it takes for the client to hear back from the server about their work would be 30 nanoseconds, because it took 10 nanoseconds in here, 5, 5, and 10. We got to 30. Throughput is the measure of the rate at which we do some useful work for a given workload. So continuing our example here with a camera that talks with some image service. The throughput on the camera might be measured in terms of frames processed per second. So the camera takes one frame, one image. So we can measure the throughput of our service here in terms of how many images get processed per second. So the camera might be able to send images across this pipeline at 1,000 frames per second. But then inside of this image processing service, these multiple phases might be slower. This phase one at 10 frames per second and phase two at 29 frames per second. So when we add these components together, the throughput becomes the minimum value. So even though this component can function at a high throughput, 1,000 frames a second, and this one 1,000 and this one 29, we're still stuck only processing 10 frames per second because of this slow phase one component in our image surface. So for our goal to design for performance, our high-level approach is to measure our system first to find which aspect of performance is lacking, be it throughput or latency. We measure each individual component to identify the bottleneck. Then we identify if fixing that bottleneck could actually realistically improve system performance. So we might have a bottleneck in the case of our image processing service in phase one. We see phase one is the bottleneck here because it's the slowest thing. Just fixing phase one isn't going to make it 100 times faster though, because phase two is still slower than this communication link. So we still have that limitation there. We'd have to look at both of them. How do we improve throughput? So let's consider this high-level sketch of what we can imagine might be how Facebook responds to requests. So when you make a request to facebook.com, there could be a whole big pipeline of tasks that have to happen before you get a response. Maybe there's some sort of cache to determine if Facebook can use some pre-existing result, and maybe it needs to build some components like a friends list and make your news feed to show up and make some list of suggestions that's going to show up on the side and then finally get the response back to you. So if we want to improve the throughput of this system, the easiest approach, given we're in the concurrent and distributed systems class, is to introduce concurrency into this pipeline. So instead of saying that we can process only a single request per second with a single cache check and a single build friends list, maybe we can do some concurrent processing where we can do multiple requests in each stage. So each stage could run in its own thread, and if a stage completes its task, it can start processing the next request right away. So our system would process multiple requests at the same time. Reducing latency, however, is usually a lot more challenging than increasing throughput. The reason for that is that we can't just add capacity. So if we would like to serve more requests at a time, if each request is independent, I could have dozens of this entire blue Facebook.com box, right? In fact, there are probably hundreds or thousands, where there are thousands of different computers that can each do any of these tasks of building your friends list, for instance, and we can respond to thousands of things at once. But what if our goal is to build this friends list faster, just to reduce the latency on that? So reducing latency is often more challenging than increasing throughput because of the different kinds of limitations that we hit. So in terms of physical limitations, when we're talking about network-based systems, we certainly run into speed of light issues. We can run into algorithmic limitations. At some point, there may just simply be work that needs to be done serially, like looking an item up in a hash table to find, for instance, some cache value. To look the item up in the hash table is fast, but we have to run this hash function to find what the hash of the item is, and it's just tough. That's not something that we can make faster. We can run into economic issues too. So maybe at least for some low-hanging fruit, we can make our system have lower latency by adding more RAM, for instance. If we have more RAM, then we can store more things in memory, less things on disk. It's slow to go to disk, it's fast to go to memory, so we can reduce the latency there, but that simply gets expensive. Here's a fun brief diversion, just in terms of how far people will go for improving latency. I'm sure everyone understands at a basic level how the stock market works, at least this one bullet, that you will win if you buy things cheaply and sell them for more. So a lot of the skill in stock trading involves in knowing what a stock is going to do before your competitors know it. So maybe you guess, maybe you have some insight, maybe you have some intuition. Um, if you're Eddie Murphy and Dan Aykroyd trading places, maybe you've gotten some nice insider information. And if you get that, you do good, you're going to be really happy, and you can retire soon and go on your yacht in the Caribbean. So algorithmic trading is a notion where we have computer programs that look at various factors and do these trades automatically. And the goal is that these algorithms can go really fast. So if my algorithm is faster than you, then I will make my purchase before you, or I will make my sale before you, and I'll get a better price and I'll make more money. Fun example, this was an NPR Politics, NPR Planet Money podcast extra. These guys wrote a simple Twitter bot that looked to see when the president tweeted positively about a company. So it would automatically look on Twitter to see if President Trump mentioned the name of some company in some positive light, and then immediately buy or sell the stock. The goal was that you get in and out before anyone, say in the news or elsewhere, finds out about this tweet because you saw it instantaneously. So this whole high frequency trading, algorithmic trading thing only works if you can make your trades before other people find out. So for instance, what if you were to set this bot up in Chicago and I set one up in New York City? The result is that I would beat you to it every time. And the reason for that is because of latency and how stocks are traded. So it turns out that most of these stocks are traded in New York. So if I'm in New York, I am closer to where the stocks are being traded, and there will simply be less latency between when I say sell this stock or buy this stock and when it actually happens. So that seems kind of crazy, right? Like the internet is the internet, things are fast and things are fast. So let's put this concretely. The speed of light is about 300,000 kilometers a second. That's fast, right? But how fast does our CPU take to execute a single instruction? Well, if we have a moderately fast CPU, like a 3 gigahertz CPU, then our CPU executes instructions every 0.33 nanoseconds. So in the time that I have one CPU cycle, that my CPU executes one instruction, light can only travel by 10 centimeters. 10 centimeters is not very much compared to the distance between Chicago and New York and back. The distance between Chicago and New York, about 700 miles, so it will take about 7.4 milliseconds. In the time that your message travels between Chicago and New York, my CPU that's sitting in New York and doesn't have to travel 700 miles can execute 22 million instructions. This is an eternity. Okay, so why is this a tangent that we're talking about? This is a tangent that we're talking about because we said that a lot of the limitations for getting latency down become economic. So we can see an example of what happens if money is not a factor in high frequency trading, or in stock trading in general, actually. So it turns out that people actually care a lot specifically about this link between New York and Chicago, because lots of commodities like frozen concentrated orange juice and pork bellies are traded in Chicago, but stocks are traded in New York. And changes to commodity prices like ethanol might dramatically impact the price of stocks. So if I see in Chicago that ethanol is becoming cheaper, then maybe I would like to very quickly, before someone in New York finds out, buy and sell some stocks that have to do with ethanol so that I can then profit off of that. All right, so we want to cut down this latency here. So sidebar, it turns out it's not quite as simple as 700 miles taking 7.4 milliseconds. You can't, it is about 700 miles as the crow flies, but there are streams, mountains, and such, so it's more like 1,000 miles. We don't actually get to send data at the speed of light. The best that we get in fiber optic cables is about 31% of the speed of light, or it's 31% slower than the speed of light. So if money is no object, what can we do? We can throw billions of dollars at this problem, which is something that has happened. The original cable that was built between Chicago and New York was about 1,000 miles, took about 14.5 milliseconds for sending data round trip. Another company then decided that they would make a cable that was shorter. So this original cable is 1,000 miles, and they said, aha, there were all these mountains in the way. You see the red cable, it kind of like jogs around. It follows train tracks. It goes around mountains. It goes around streams. The guys who built the green one said, you know what? Let's just blow up mountains and build this cable so that it'll be 200 miles shorter. They shaved off 1 millisecond and made a ton of money building this very expensive cable because everyone wanted it because it was faster. Then these other guys came in and said, aha, 825 miles. If we do it using microwave beams through the air, we can actually go even faster because of the curvature of the Earth, and we can go straighter, and now it only takes 9 milliseconds. Now there are people who are building another system that shaves off even half a millisecond off of this other microwave approach. Buying access to use this thing costs hundreds of thousands of dollars a year. People pay a ton of money for this. We don't have this at our disposal, though, and this is not a generic problem for latency. So we don't have this money. What we want to do, and what we're going to talk about in this lecture mostly, is reducing latency using concurrency. So our approach could be to take our whole system here that we had, our Facebook request that went through this whole pipeline, and maybe we can parallelize some of it. We can build our news feed at the same time that we build our suggestions, and then they won't be serial. Overall, though, our process is still going to be limited by the serial section, right? So we make it a faster latency now because we can build the newsfeed at the same time as building the suggestions. But we still have to build the friends list maybe before we can make the newsfeed and before we can make the suggestions. So because of that, we still have this limitation. We can't get to the perfect time. So these examples are at a very high level, right? we're looking at components and some big server system, kind of playing it a little fast and loose there. For the rest of the lectures, we talk about improving performance with concurrency and cutting latency. We're going to focus on smaller, more concrete examples. So we're going to drill all the way down and go way down the rabbit hole. Instead of talking about a high-level architecture, I'd like to talk about matrix multiplication. Thinking about how to multiply two matrices in parallel. Reminder. So if this is the notation that we use for matrices, right? So Cij means that we're talking about the element in matrix C at position I comma j. So the product of multiplying two n by n matrices, A and B, is going to be given by this formula. We take the product of each of these pairs in the matrix, and then we take the summation over that. So here's a worker thread that computes this matrix multiplication. The worker in position I comma j, row, column, is computing the final value for that position I comma j. So note here that what we've got is a thread, meaning that this worker is going to run concurrently with other threads also. So we want to do this thing in parallel. So I'm going to make one worker for every row comma column. So in an n by n matrix, I'm going to make n squared workers. And each worker is going to work on computing just a single element in that final matrix. The actual computation happens down here in that run method, right? So the worker thread gets started, its run method gets called, and it's going to compute that product in there. Here's the driver code. So our driver code to multiply some matrices is going to make a matrix of workers. So for our n by n matrix, we'll make an n by n worker array. We fill our worker array with n by n threads. So we'll make a new worker for each element. We start every single one of them, and then we wait for them to finish. Now, I will assure you that this code works, but it's not great. There are some issues that kind of prevent this from becoming an ideal design. What's good, right? This program is highly parallel. I have this n by n computation, and I make n by n threads. So it's literally composed into as many different threads. I'm going to get as much parallelism as I can. That's good. Is this bad because I'm stuck waiting in locks? I didn't remember seeing any. I mean, look in here, right? Each worker thread, here's our code. No locks, no synchronization. Each worker thread just computes some result and stores it. So we have to step back a little bit maybe and see some new concepts about why this is, in fact, a very bad design that we should not use. So in practice, while this design might perform nicely on small matrices, it's going to perform extremely poorly for matrices large enough to actually be interesting that we would want to parallelize them. And here's why. Threads require a memory for things like stacks, right? To store all of the local variables that each thread has, that takes some space, and to keep track of what code each thread is running, that takes space. There's other kinds of bookkeeping stuff that has to get stored for that too. There's overhead that's coming from the system scheduler. Remember we talked about in processes versus threads that threads were faster to make and threads were faster to schedule than processes, but they're still not free. There is still some overhead that comes from doing this. Creating lots of short-lived threads is a very inefficient way to organize this multi-threaded computation. So a much more effective way to organize a program like this is to create a pool of long-lived threads. So for our n by n matrix, instead of making n squared threads, why don't we instead say for our computer that has k processors, let's make k threads. And then we're going to assign each of those threads to some short-lived tasks. These thread tools can be platform dependent. So it makes sense for these large scale multiprocessor systems to have big pools, and my old laptop with only 2 processors to have a smaller pool. Thread pools avoid this overhead cost of creating and destroying threads in response to these really short-lived functions, like computing each element in the array, in the matrix. In addition to having these performance benefits, thread pools have another pretty important, but maybe less obvious advantage, which is that they insulate us from any kinds of platform-specific details, like how many concurrent threads can actually be scheduled efficiently. We can write this matrix multiplication code that will work as efficiently as possible on a machine that only has 2 processors as on a machine that has 100 processors. Thread pools make it possible to do this by having the simple interface hiding the complex platform-dependent engineering trade-offs. So we've already started looking casually. I think we saw at the very beginning of the semester, this executor service. We just saw it kind of out of context, like here's a way that you can run a thread. Today we're going to talk about executor service and especially how the callable implementation works in much more detail. So the executor service gives us this ability to submit some task and then to wait for the set of submitted tasks to complete and also to cancel them. If we want to run tasks that have no return value expected, then we can pass to our executor a runnable and say that the task is runnable, which just has a run method, no return type. If there's something that our task is going to do and we need the result back, then we use a callable object. And callable is this generic type. So remember this syntax callable t. T could be any type here. So if a result value of type t is expected, then we use a callable. The executor calls the call method, which returns that type t. And what's particularly interesting here, and something we'll focus on, is how we get the return value from that call. Because it's a little funky, right? Because we say execute this task, but it goes off and does it in the background. So how do we ever find out about what the return value is? So here's how to use an executor service to compute some value asynchronously in a background task and get the value back. So I've created my task and it's a callable. And then when I submit that task to the executor, notice that actually submit returns something. Submit returns a special kind of object called a future. And for a callable that returns a type t, the future also is parameterized by that same type t. So this future object has a method get, and when we call get blocks, so it waits to return until that value becomes available. So what's going to happen concurrently here is when we call executor.submit, somewhere in the background, perhaps in another, or surely in another thread, our task is going to start running. The other code that may exist between calling submit and get will run in this thread. And then when our thread here gets up to calling the line highlighted, calling the get method, if that task has completed, this will just return the value right away. And if that task has not completed yet, then it's going to wait until it is completed. It's like saying wait for that task to complete. Note also, we might have seen this interface too, where we submit a runnable to the executor also. That still also returns a feature, but not one that has a value on it. And if we want to wait for a specific task to finish, we can call .get, which is going to simply block until the computation is complete. So an important thing to understand here is that creating tasks and sending them to an executor are really suggestions. They're not commands. In fact, we have no control over how the operating system is going to schedule our threads or schedule our tasks. So this is maybe like traffic signs if you're driving out in Maryland, right? Sorry, apologies to any Maryland drivers in the room, but we live in DC and see plenty of them. The executor is kind of like the Maryland driver. They can see the traffic signs and they could follow them, or they could avoid them. So in the context of our executor, we might hope that all the tasks happen in parallel, but they could totally just happen sequentially. All right, so let's zoom back down into our matrix example and look specifically at the addition part. So how we can take this matrix addition and do it in parallel. In the text, if you're interested, a lot more details, especially on matrix multiplication. So we can decompose this matrix addition to get each of these C0, C01, all 4 values in C, as doing 4 parallel additions, right? Each element C00 is composed of A00 plus B00. C10 is composed down here, so on and so forth. So let's look how we can do this matrix addition using a thread pool. So note the Java code here, not real Java code. We have simplified this so that it fits on the slide, and especially things like subscripts, you can't do in Java. You can look in the book for the detailed working code. So what does our add task look like, right? First off, it's a runnable. It's going to just add some stuff. It's not going to return it. In a base case that we call add and have a single dimension array, we simply do the addition. We compute that element of C from that element of A plus that element of B. But if we don't have this single dimension array, then we partition that matrix into half-size matrices. So we'll split it in half. And then we'll submit 4 tasks for each one of those halves. We split it in half vertically and in half horizontally, so we get 4 tasks in total. And then we wait for each one of those things to finish. So the high level here, right, is we'll make a task overall for the matrix, and then we'll make a task for each quadrant. And we'll do that recursively. So this matrix example uses features only to signal when a task is complete. We were using the runnable interface. Features can also be used to pass values from completed tasks when tasks have dependencies. In the matrix example, we didn't need the results of one task to complete another. We just made one task that computed each individual cell in our combined matrix, and it didn't matter what other cells in the matrix came out to be. We could complete those things independently. To illustrate a different use of feature, we can consider how to decompose Fibonacci into a multi-threaded program. So remember that Fibonacci sequences have this dependency structure where we can recursively define the Fibonacci number for some given number n as 1 if n is 0 or 1. And if not, it becomes recursive. So it becomes the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So if we want to take this thing and make this thing parallel, we're going to have to manage it somehow so that dependencies between Fibonacci number of n and n minus 1 get managed so that we can still do things in parallel, but we can't compute some number until we compute the number of its children. So disclaimer, the implementation we're going to go through in these slides is horrifically inefficient. Do not use this. But it illustrates our point of how to deal with dependencies. The reason why it's inefficient will become clear momentarily, and it's because there's no caching of values that we recompute. Multi-threaded Fibonacci implementation. We have our Fibonacci task, which implements callable, and each Fibonacci task call method will return an integer. So our call method is going to be dependent of what it does on what number n we made for our Fibonacci task. In the base case, we'll return 1 for n equals 0, 1, or 2. For n greater than 2, we define Fibonacci recursively and asynchronously using multiple threads. So recall that the Fibonacci number of n is the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So we'll create tasks to get the Fibonacci number of n minus 1 and to get the Fibonacci number of n minus 2. We submit both of these tasks to our executor and get the futures that represent the value that we'll get back when they eventually finish. Then to get our Fibonacci number of n, we'll return that first part, n minus 1, plus n minus 2. And recall that these get methods are going to block and wait until the child task finishes, and then return that original value. Okay. So again, why did I say this is horrifically inefficient? This is horrifically inefficient because we'll recreate multiple Fibonacci tasks for the same number many times as we go down this list. There's no caching of that intermediate value. So how much performance do we get for our Fibonacci calculation compared to a serial implementation? Formally, we can model this multi-threaded program as a DAG, as a directed acyclic graph, where each node in the graph is one step of the program. And that graph unfolds dynamically as our program is running. So a thread in this model is going to be the maximal sequence of instructions that doesn't include spawn, synchronization, or return statements. Each node in the graph is some instruction or some execution of some method, and it's a single unit of work. So here's the DAG, the directed acyclic graph, for our multi-threaded Fibonacci program. Each circle in the graph represents a thread, circles. Each black horizontal arrow is a sequential dependency. The code says to do this before that. So to get the Fibonacci number of 4, first we have to get the Fibonacci number of, here's the Fibonacci number of 4. But to get that, first we have to get the Fibonacci number of 2. And before we get that, first we have to get the Fibonacci number of 3. So each of the blue circles is a thread, it is a task. And these are those sequential dependencies. To get the Fibonacci number of 2, first we have to get 1 and 1. The red downward arrows represent these spawn calls, calling out to our task again. So to get the Fibonacci number of 4, well, first we have to get the Fibonacci number of 2. And that invokes this new call. The green upward arrows here represent when the child thread rejoins the parent. So in this graph, we want to get the number of 4, but first we have to get the number of 2. So we make a new thing to get the number of 2. But here's the number of 2, sorry. But to get the number of 2, first we have to get the number 1 and the number of 1. And then we do that. That returns. Now we have the number of 2. That returns. And this all gets compiled. So we can see how the DAG unfolds over time. We want to get Fibonacci of 4. Well, we have to get Fibonacci of 3 and 2. We want to get Fibonacci of 3 and 2. Well, first we have to make out those calls as we go down. So the reason why we draw these dependency graphs and show all of these different calls and the different threads and their dependencies is so that we can decide if we did a good job making this thing parallel or not. What would it mean? What would this graph look like if it is sequential versus parallel? So we need to start off by defining what work is. So we want to make work concurrent, right? So what is work? We define work as the total amount of time that we spend on a single processor. So there is some critical path length of something that has to get done on a single processor. And it's not going to be possible in our parallel algorithm to beat that because this is just the one sequential part that has to happen on a single processor. So if we return back to our graph, this DAG showing all of the dependencies for the Fibonacci computation, we can answer this question. How much work does Fibonacci of 4 take? To do that, we just need to count the steps. So what do I have to do to get Fibonacci of 4? Well, I have to do these 17 steps. 1, 2, 3, we call it down and we go through this. We have to do 17 different calls here. But what's the critical path for Fibonacci of 4? That's going to be the maximal length. So what is the worst case thing that could cause a processor to be slow here? Well, that's going to be this call chain here. This is the longest single chain of calls that we have to wait for at the top level. So to get the Fibonacci number here, we have to go here, 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 and all the way around. This requires 8 steps. Our critical path length is 8. So it's convenient while we talk about these different performance and parallelism tasks to just throw down a little bit of notation. So we'll say TP is the time that we spend on P processors. So if we fix P to be 1, then we're going to call the amount of time that it takes to run on a single processor the amount of work. So if I had no parallelism, this is what would happen. And this is the total amount of stuff that has to get done. The critical path length, T infinity, is the time that it would take for our task to get done on an unlimited number of processors. So we're probably going to be somewhere in between when we actually concretely run this. But to analyze this algorithm and this software to determine, quote, how good the parallelism is, we're going to look between this spectrum of it happening on a single processor sequentially and what that critical path length is, like how fast it could get. If we have infinite money and we can buy infinite processors, no matter how rich we are, this critical path is still going to limit how quickly we can run this. So a few simple observations. First, buying P processors is not going to speed up our application by anything more than a factor of P, right? Another way to think about this is that P processors can do at most P work in one step. So we can't possibly speed things up faster than having our work perfectly distributed amongst all of those processors. But also, the time to execute the program on those P processors can't be less than the time to execute the program on our infinite number of processors. So there's no way that we can beat the infinite resource argument. So if we model things in that infinite resource world, we know that we're looking at the best case scenario. All right, so why the notation? Now we want to talk about what the speed up is going to be from our maximum possible approach of parallelizing things really well. So the speed up on P processors will be the ratio between how long it takes with a single processor to do our work and how long it takes to do all of this work with P processors. So programs with long critical paths will have worse speedups than programs with shorter critical paths. We say that a program has this linear speedup if it's proportional to the number of processors. And this is the best that you can do, right? That as I add more processors, the speedup goes up linearly. Sometimes you hear people talking about superlinear speedup. We're using P processes speed up a computation by more than a factor of P. This phenomenon happens sometimes with parallel searches where the first processor to find a match halts the computation. So adding more processors might increase the likelihood that your algorithm will happen faster. For most kinds of algorithms that we're going to be analyzing, though, linear is the best that we're going to get. So the maximum possible speedup then is going to be the ratio between the work, which is the time it would take to do this on a single processor, and that critical path length. This quantity, maximum speedup, we also call this the average parallelism or just the parallelism. So now let's go back to our matrix addition to talk about what kind of parallelism we got here by decomposing this into these 4 parallel additions. So let's see if we can analyze the running time for adding 2 matrices using this model. So we'll define this function A of P to be the running time for adding 2 matrices n by n in our process model. 2 special cases of interest are, again, for one processor or infinite processors. The time that it takes to run on a single processor is our work. The time that it takes to run on an infinite number of processors is our critical path length. So what is the work? What is A sub 1? It's relatively easy to compute. So if we need to add 2 n by n matrices, we're going to split it in half twice, right? So we need to add 4 half-size matrices. That's the main work. Plus, there's probably some additional constant time work that has to happen to do this addition, like maybe partitioning the matrix and splitting it up isn't free, right? But it is some constant cost that doesn't vary with the size of the matrix. So we can solve this recurrence using standard methods, and as it turns out, the total overall work for adding 2 n by n matrices is about n squared, the same as a usual double loop summation of not doing anything in parallel. If we were just to do this matrix addition normally, it would be an n squared algorithm. So the fact that our single processor but multi-threaded algorithm still is n squared, that's reassuring, because if it were better, then probably it would be broken. And if it were worse, then it would be horrifically inefficient. So computing the critical path length is a little bit different from computing the work in one important respect, which is that we can have all of the parallelism that we want. So in this case, we'll say that all of the half-size additions are done in parallel. So because they're all done in parallel, we only count 1 half-size addition and not 4. Because we no longer need to wait for all 4 to finish. We had to wait for all 4 to finish when we only had a single CPU. If we have infinite CPUs, all four can run at exactly the same time no matter what. So all infinite tasks can run infinitely concurrently. But then we still have that partition and sync time. So here too, if we solve this recurrence, we'll discover that the critical path length is quite short. It is in fact logarithmic in n. So comparison, critical path length is log n, total work was n squared. So there's a very large amount of parallelism inherent in this problem that this algorithm is exploiting. Let's look at matrix multiplication again also and think about it in terms of what kind of parallelism speedups we can get. So the approach here was to split each matrix into submatrices and then solve the problem in the submatrices. And then that happens recursively again and again and again, right? We keep splitting this thing up into multiplications. So first, there are these 8 multiplications that have to happen for each one of the terms, and that those multiplications can happen in parallel. After those multiplications occur, we're not done. We have the second phase, which is the additions. And those additions can also be done in parallel, but we can't do the addition, adding this term and this term, until after this multiplication and this multiplication are done, right? We can't have to still follow the order of operations. So the work required, well, we have to do some parallel multiplications, each of which is half the size of the input. We have to do 8 of them. So we have 8 parallel multiplications plus adding all of those results. So the work to do multiplication of a matrix of size n was 8 times the work to do multiplication of a half size plus an addition of that size n. Because we're just measuring work here in this one processor scenario, we don't care about the parallelism. So if we solve this recurrence, then we'll find that this turns out to be n cubed. Again, this is the same same time bound that we get for just doing this sequentially in a triply nested loop. To get to the critical path length, we'll compute this again by assuming that our multiplications can all be done in parallel. So we lose that term 8 here because we'll assume that all happens at once. We only pay for the cost of the multiplication once of one of those. And we still have the cost of doing the addition too. But we'll consider the cost of the addition assuming that it happens infinitely parallel also. So if we solve that, well, we worked through already how the cost of doing the addition of size n is actually log n. And then if we continue to solve that, and we solve our multiplication, the critical path length is going to be about log squared n, which is also pretty small. Now here's something very interesting. So remember that parallelism was the ratio between the program's work and its critical path. It was roughly a measure of how many processors we could keep busy on this kind of problem. For matrix multiplication, the numerator was n cubed, and the denominator was log squared n, which is pretty large. So for example, to multiply 2,000 by 1,000 matrices, we get a parallelism of about 10 million. Notice how logarithmic division works. This calculation suggests that we can keep roughly 10 million processors busy multiplying matrices of this size. Of course, this vastly exceeds the number of processors we're going to find on any real machine any time in the well, probably for quite a while. So this calculation also gives us an idea why computers for very numeric computations like those that do meteorological calculations, can have thousands of processors because these problems have really a lot of parallelism that can be used. So the more processors, the better. However, there is kind of an asterisk here. We have this thing with 10 million times parallelism, right? Can't we just build this 10 million parallel computer? Um, no, is the answer. And in fact, the entire scheduling operation about how many processors we get simultaneously and how they talk to each other is really tricky and something beyond the scope of what we can talk about in this class. And really, you could go really deep having multiple PhDs and getting them in computer architecture and operating systems to see how this works. But at a high level, we don't have computers with tens of millions of CPUs because coordinating between them is really tricky. And even on our own computers, like if your laptop has 8 cores, if you write a program that has 8 threads, you have no guarantee whatsoever in terms of how many processors your application is given at any point. The operating system is going to mix together lots of different threads from lots of different processes that are going to come and go dynamically and be running them on some number of processors at any given point. Your application will not have direct access to those hardware processors. So this is mostly just a footnote here because we have been talking this lecture so much about ideal parallelism in this infinite case. We just need to understand that the kind of parallelism that we'll get will vary with how many processors you actually get when your program actually runs. So if we do a very intensive evaluation and find out that we should be able to easily get an 8x parallelism, should see this 8x speed up, but then we run it on our computer that has 8 CPUs, we might not happen to see that happen just because those CPUs went to other tasks that were running concurrently. Before we finish up today, I want to jump back to the topic of future programming that we introduced a little bit in today's lecture when we were talking about the executor. So Java's future is kind of an implementation of a generic asynchronous programming model called promises. And starting in Java 8, there's a extended version of future called completable futures. We're going to talk about completable futures. So futures in general, promises, are really nice in designing tasks where we would like something to happen in the background and be notified when it's done and get that result back. So note that instead of using futures, we could have implemented all of this stuff with submitting tasks and getting their results using some combination of synchronized and way to notifier conditions. Promises are an extension of just the future, and completable future is an extension of future, where we can chain together different asynchronous tasks that happen in the background. So here I have our code snippet of creating a completable future. The creation of completable futures is very similar to making a future from the executor. Completable future.supply async is going to ask that this asynchronous task gets executed by the executor, but we're going to get a completable future back instead of just a future. Why is this important or interesting? Completable futures can be chained together. In our code snippet here, we're going to create an asynchronous task, this completable future supply async. And in the background, when this thread starts, it's just going to sleep for a second. And then after it's finished sleeping, eventually it's going to return a string John. This is a little bit contrived, but maybe gives a good example for how we can chain futures together. So this is going to return John eventually, but we want to have some other task happen when that's done. So we can create another future that's changed to the first future. So I'm going to create a new completable future. Here we're going to call it greeting future. And the way that I create it is by saying after that other future, after what's your name future is done, when it is done, then apply this other function to it. And we're going to pass to our new future the return value from the old one. And what this task will do is return the string hello, comma, and then whatever the return value was from the prior future. Now we can still do that same pattern where we call get. That's going to block and wait until this future finishes. But we see that now this greeting future will wait to finish until after the what's your name future finishes. And these things get chained together. So chaining together asynchronous events can become really useful when we need to do processes that happen in the background but have lots of dependencies. So for instance, we could maybe create some completable feature that promises to get some data and then promise to make some changes to that data. And then when that's done, report on all of those changes back to the user. We can also specify kind of nicely using this completable future API that if there's an error in any one of these tasks, which could happen in different threads and in different orders, to report that error in one place. We could also add multiple things that should happen concurrently and try to combine those things together. Completable futures can be used really in any case where you have multiple things that happen in the background but care about the result and care about them happening in some order. For instance, if you have to asynchronously read or write data, like we would like to read some data that comes in from a web service and then process it and then save it into a file. We're going to see more with completable futures and we'll start writing them over the next few weeks. I just wanted to whet your appetites now as we're talking about these concurrent programming models. So just a reminder as we wrap up today's video that homework 2 is something hopefully everyone is working on. It's due on March 4th, so we still have another week of classes to talk about it. I hope everyone had a good snow day and has a nice weekend. I'll see you all on Monday.